Okay, so the whole test is only 12 questions, so it's really important that on each question you do well, right? Because partial credit is great, but if you get a few points off every single problem, that's not a good situation. There's only 12. And so whenever it says things like solve algebraically, that means it's really important that you do it the way I'm asking you to do it. Algebraically just means don't graph it and get the answer. You have to show some work in order to get it. So I see this personally and I say, hey, I can set these equal to each since they both are equal to y. So x cubed plus x squared equals 5x squared. And then the way to solve something like this algebraically is you get everything on one side and then factor. So subtract 5x squared and get x cubed minus 4x squared equals 0. To factor this, they have an x squared in common, so we take it out and it leaves us with x minus 4. And then finally we set each part of it equal to 0, and that gives us our x value for this problem. So x squared equals 0 means that x equals 0, and it doesn't matter that it's squared, it just tells us one of our answers is x equals 0. X minus 4 equals 0 tells us that x equals positive 4. But solutions in the case of systems, remember, are points if we have x, y, and so we need to plug these back in somewhere to get what y is for each of these x values. So I like the second one slightly better personally, because then we're only having to do one or two things depending on how you look at it. So for 0, that's easy. 5 times 0 squared is 0, so that's the point of 0. For 4, y equals 5 times 4 squared, so 4 squared is 16, and 5 times 16 is 80. So that is the point 4, 80. Now I will pause, because maybe I might have gone through that too fast. Does that make sense, that process? Yeah. Okay, the problem on the test is going to be very, very similar to that. Very, very similar. Okay? At the end, yeah, we found two things for x, and we need y's that go with them. So we plug in 0, and you can plug it into either equation. And so you plug in 0, and you get 0, so that's a 0.00. Okay. And then you plug in the other answer, we got 4, and you 4, 80. Now, because you'll have your calculator, you could graph these really easily and check to see if that makes sense. You should definitely have an intersection at 0, 0. Then you'd have to probably mess with your window to see the one that's at 4, 80. Or you can plug them back in to check. Any other questions on this one? All right, so the next one is number 4, where we are solving graphically. So we'll need our calculator for this. And the problem is 3 to the negative x is one of them. I'm in the wrong mode. And what's the other one? 3 over x? Negative 3 over x. Negative 3 over x. I'm zooming standard. I may not, oh, okay, there we go. Phew. So we're just graphing the two equations together, and then we want to find a point of intersection, and that only happens one place, this graph over here. And so you have to do second trace and go down to intersect. And then it depends on what kind of calculator you have, but in general it asks you to specify what graphs you're talking about. We only put in 2 graphs, so it's going to automatically pick what we want. But because of the way this graph is, how we have like asymptotes over here, it is helpful after you do first curve, second curve. Well, for second curve I have to move, right, because it didn't give me an actual number when I started. If this is what your second looks like, where y doesn't have a value, you have to move it somewhere. All right, so now when I guess, it's helpful for me to sit here and move it closer to the intersection, because otherwise it might get confused about what you're asking. And when we guess, it tells us -1, 3. So that would be our answer on that one. And you don't have to show any work on that. It's just that's the answer, -1, 3. Now let's say hypothetically that instead of what we have, what if we were given that one of our equations was x squared plus y squared equals, I don't know, something like 10. Okay? Then we have to solve this for y to start off with, right? So we have to subtract x squared from both sides. And then to get y squared to just be y instead, we square root. And here's the super important thing. That means that this is plus or minus the square root of 10 minus x squared. So you have two different y equals that you have to put in. And so when you're doing that on your calculator, you literally just, in like y1, put positive square root of 10 minus x squared. And in y2, you'd put negative square root of 10 minus x squared. And if you graph those together, one of them makes the top half of a circle and the other one completes it. And so then, let's say maybe a line intersects that. We would have two intersections that we would have to find. And we did that sum in 7. Whatever section this is from, 7.1. So go back and look at those problems in 7.1 where we graphed and make sure that you can get those answers. If you want to, hypothetically speaking. I'm not saying it's going to be like that on the test or anything. Questions? Okay. Find the matrix product by hand. So you'll have your calculator. Hopefully you have figured out how to do this on the calculator. If you haven't already, then we can look at that. But if I ask you it by hand, that means I need you to be able to show me that you're doing it by hand. So what I mean by that is I need a matrix where you show the steps you're taking, where we do, remember we do the first row in the first column, so we do -1 times 0 plus 3 times 1. Like, that's the work I'm talking about you showing. Okay? And this is going to show me, hey, you're really doing this by hand. You didn't just plug it into your calculator. Because I know some of us can sit here and do it in your head and just write the answers, but that doesn't help me know that you really did it without your calculator. So we would just through and do each one of these. -1 times -2 plus 3 times -3. And then first row, third column. And then the second row has the second row in each column. So 5 times 0 plus 4 times 1. 5 times -2 plus times -3. 5 times 6 plus 4 times 2. And we mentioned in the notes in the video that there's this pattern happening, like here, look how I have 0s and 1s in common, -2s and -3s in common, 6s and 2s in common. The numbers in front, each of these looks like the first matrix, -1, 3, 5, 4. -1, 3, 5, 4, and -1, 3, 5, 4. So now we would actually do multiplication and addition and stuff and get 3, 4, -7, -22, 0, 38. And if I did any of that wrong, please tell me, because almost 8 o'clock in the morning, a little early for mental math, maybe. Is that recording you? Yes, it is. Yeah. No, not my face, just my voice. Sorry. How does it connect that to writing? Like my computer right now is recording the screen and it's recording my voice because I'm wearing a earpiece that's connected. It's pretty fancy, I think. Yeah. Any questions on this one? it's going to be very similar to this. You just have to remember the steps. Hint, wink, wink, nudge, nudge. Determinants by hand. So again, there is a way to do this on your calculator. I hope you know how to do it. You can check your answer. It would be great to be able to do that. But to show that you're doing it by hand, you either need to do the thing with the diagonals or the cofactor thing. That we did it both ways in the notes. I kind of think it's easier just to explain the diagonals, where you write out the first two columns again, and then we're looking at the diagonals going this way. I don't know. Okay, so 3 diagonals, so 8 times 7, and now I can't read what the matrix says. 2. 8 times 7 times 2, plus 3 times 9 times 6, plus 8 times 2 times 5. That is the diagonals going one way, so we add those all together, then we take the diagonals going the other way. So 6, 7, 8, plus 5, 9, 8, plus 2, 2, 3. And you find these two numbers and then you subtract them. So the first one gives you like 354, and the second one gives you 708. It gives you 708, and then we subtract them. Okay, because that's what you do it with this process. Is you take the diagonals one way, you subtract the diagonals going the other way. So you get negative 354. And it may freak you out that that's a really big number, but that was a lot of multiplication that we just added together. So that is a reasonable answer. It's super helpful. Some of these numbers are zeros. That makes this a lot easier. But none of these were. So that's why we got such a big number. Questions on that? Use elimination. So the big thing on this is off. The idea is you want to eliminate the same variable twice. It doesn't matter which one you pick in this case. I like y personally. Z would be equally as easy to eliminate. But if I want to eliminate y, and start off picking the first two equations, and you just have to add them together. They're already perfectly set up to eliminate. The y's go away, and you get 2x plus 2z equals negative 14. And that's great. We just got closer to our goal, but we still need another equation that just has x and z. Come back up to our equations, and now I'm going to use the first and the third one. Okay, I could do first and third or second and third, and it doesn't matter, but the first and third is already set up to eliminate, so that's why I'm picking those two. And it ends up having the added benefit that both of these cancel out, which gets us to what we need faster. X plus x is 2x. Negative 5 minus 3 is negative 8. Divide both sides. Divide both sides by 2, and you get x equals negative 4. Okay. If we had gotten x and z left here, like if the z's hadn't canceled, we would set up a new elimination problem with those two equations, x and z. But since we got x by itself, now we plug in to this equation that we have that just has x and z. So that's 2 times negative 4 plus 2z equals negative 14. This will be negative 8 plus 2z equals negative 14. And then add 8 and divide by 2. So z is negative 3, and then we have to take these two things and plug it into one of the very first ones up here. So it doesn't matter which one you pick. I like the second one because all of the variables have positive coefficients. So negative 4 plus y plus a negative 3 equals negative 9. So add like terms on this side and get y minus 7 equals negative 9, and that means that y equals negative 2. And our point is negative 4, negative 2, negative 3. And that's our answer. Keep in mind that you can check this on the calculator really easily by plugging this in as a matrix, the original thing, plug it in as a matrix, and then remember that you can do RREF of whatever matrix you choose to put it in, and it should tell you that the answer is negative 4, negative 2, negative 3, so that you can check yourself. But most of the time, if you get an answer that's not fractions, you probably did it right, just because that's the nature of a problem like this. The next one is like 16. 16 is really unpleasant, and I'm probably not supposed to say this, but I'm honestly okay if you just write number 16 straight from the review or from the video. So instead, we're going to go over 33 from 7.3, because this is a more realistic situation. By realistic, I mean more likely to be on the test, not realistic is likely to come up in the real world. And I'm doing this instead of 16. And on the instructions, it does say that you can either do row echelon form or reduced row echelon form. So this is your preference, which one you want to do. The difference is how many steps you do inside of your matrices. So if you're not a fan of this, you might just choose row echelon because it's simpler. That's the one where you have ones in your diagonals, zeros, and these are all numbers. Okay, and then once you get that, you have to take z and plug it in, and then take y and z and plug it in. If you're doing reduced row echelon form, you get everything on this coefficient matrix except for diagonals of ones to be 0, and then it tells you x, y, and z at the end. Okay, so for this problem in the book, we only had to do the first way, but we're going to go all the way to the second one. You always start with the first column. Well, actually, let me write my matrix. You always start with the first column, trying to get a 1 in the top left. Hooray, we've got it. So that's done. And you use that 1 to get the zeros underneath it. So you should be thinking, hey, what could I do to 2 to make it be 0? I could subtract 2. That would make it be 0. But we're not just allowed to subtract 2 from a row. We have to do negative 2 times row 1, and we have to add it to row 2. That's steps we're going to take. And this is basically us doing an elimination problem. Okay, we're going to take everything in this equation and multiply it by negative 2 and add it to this other equation so that we can eliminate our x's. So that gives us negative 2 times 1 plus 2 is 0. Negative 2 times negative 2 is 4. Plus 1 is 5. Negative 2 times 1 is negative 2. Plus negative 3 is negative 5. Negative 2 times 8 is negative 16. Minus 9 is negative 25. The first row doesn't actually change, we just used it. And I'm going to go ahead and get the 0 in the third row as well, so I don't have to rewrite my matrix a whole other time. Here, instead of subtracting something, it'd be helpful if we added 3. So we're going to do 3 times row 1, and we're going to add it to row 3. So we go through and do 3 times 1 is 3, minus 3 is 0. 3 times negative 2 is negative 6, plus 1 is 5. Right? Yeah? Okay. 3 times 1 is 3, plus 3 is 6. 3 times 8 is 24, plus 5 is 29. Okay, so now, I didn't mean to write this down here. This is up here between those two matrices. Now we're done with our first column. And so everything we do from here on out is governed by the fact that we don't want to mess up the first column. Do you have what's up? For the first column, you always use the top row because that's the one that has the 1. Okay, and we can try to mess with stuff like, we could try to do something more complicated, but this is the way that's always going to work out. It always works if you use the first row to get these zeros. And then it will always work after we get this U1 here, we'll use that to get those zeros. Okay, this is a really like methodical way of doing this. If you understand the method, it do the exact same thing. Okay. Here we want this to be 1, and so to do that, we need to basically divide things by 5 in that row. Okay. So what we're going to say is 1/5 times row 2, because that's the same as dividing by 5. So that's the only thing that changes. So -5 divided by 5 is -1. -25 divided by 5 is -5. Is it warm in here, or are we okay? I'm going to take that as okay, so let me know if that changes. Once we have the 1, now we're going to use row 2 to get row 1 and row 3 to have zeros. Because that means that we aren't going to mess this up. So here I need to add 2 to -2. So that's 2 times row 2. I'm going to add it to row 1. So this time row 1 does change. So 2 times 0 is 0, plus 1 is 1. So we didn't mess anything up. 2 times 1 is 2, plus -2 is 0. 2 times -1 is -2. Plus 1 is -1. 2 times -5 is -10. Plus 8 is -2. The second row is going to stay what it was. And then this is if we're doing reduced row echelon form. Otherwise, I wouldn't do that 0. You'd skip that part, and you would now you would get the 0 that's right here. So I would do 5 times row 2. And add it to row 3. So that would be 5 times 0 is 0, plus 0 is 0. 5 times 1 is 5, plus -5 is 0. 5 times -1 is -5, plus 6 is 1. 5 times -5 is -25, plus 29 is 4. And actually, it would be kind of nice if we did row echelon form, right? Because now we're done. Like, we got this 1 here. Technically is in row echelon form, even though I went in a little extra and got a 0 up here. You could stop here and say x minus z equals -2. In fact, let's do that. This is x, no y, minus z equals -2. Y minus z equals -5. And z equals 4. So you know what z is, you just plug it back into these other two equations and you get x and y. So y minus 4 equals -5. You just add the 4 over and get y equals -1. And then the top equation, x minus z, which is 4, equals 2. So you add the 4 over and get x equals 2. So that's the point 2, comma, -1, comma, 4. Or we could have kept going and we could have done more row operations to get these two things to be 0, which wouldn't have been hard. We actually just would have done row 3 plus row 1 and then row 3 plus row 2 without even having to multiply. Yes. The 3 ones here and zeros underneath for it to be in row echelon form. questions? All right, so partial fraction decomposition, this is 20. And we have to factor here to start with. This is x minus 3 and x minus 2. And once we know what it is when it's factored, if it's something linear on the bottom, linear meaning like mx plus b, then that means we just need to put one letter on top, like a. And then we figure out, hey, what would I have to multiply by in order to get common denominators? So this one needs x minus 2, and this one needs x minus 3. So that we just take the numerators now and write them out. 13x minus 31 equals a times x minus 2 plus b times x minus 3. So I think the easiest way now, because we know we can solve this and get a 0, x minus 3 equals 0, you can solve and say that's 2, you can solve this one as 3. If we plug those numbers in, we'll end up figuring out what a and b are. So when I plug in x equals 2, I plug that in everywhere for x. And the reason that's so great is because right here that cancels. And so we just have 26 minus 31, which is negative 5, equals negative b, which means b equals 5. And then we do it for 3, x equals 3. And you could plug in b as well, but we're not actually going to have to because b is going to go away. Minus 3 is 0, so that goes away. So this is 39 minus 31, which is 8, equals a, and then we need to write it out. So a is 8 over x minus 3, plus is 5 over x minus 2. You could check that by taking the original thing you have and putting it in equals, and taking your answer and putting it in y equals, and they should be the exact same graph if you did it right. Because we're saying those things are equal. Next, we're going to look at 22. So this one has the issue of this is not linear. Okay, it's called an irreducible quadratic. You cannot factor x squared plus 6, and so that means that when we write this out, for that one we need bx plus c. We need something linear on top because there's a quadratic on bottom, a quadratic that we can't get rid of. And so now, after we multiply to get our that's wrong. Just kidding. After we multiply to get our common denominator, the easier way to do it is to actually FOIL out and then compare what's on the left side to the right side. So negative 4x squared minus 5x minus 69 equals, I'm going to distribute the a and then FOIL the second part. So that gives me bx squared minus 3bx plus cx minus 3c. And now you can kind of think of it like terms, because if I have an x squared over here and I have some x squareds over here, because this is equal, all of that has to actually be out. That if you add ax squared and bx squared together, you should get negative 4x squared. And so what we do is we basically get rid of all of the x squareds and say that this is negative 4 equals a plus b. Well, that's not enough information to figure out A or B, so we just keep going. Now we'll do the x's. So negative 5x has to equal negative 3bx plus cx, and so that means I have negative 5 equals negative 3b plus c. And then last, we're going to do just the number. Negative 69 goes with 6a minus 3c. Now, this is a system of equations, and so you can either do this by hand, or we could actually type this into our calculator into a matrix, and we could solve it as a matrix, where we would have to do like 1, 1, 0, negative 4, 0, because this doesn't have an a, negative 3, negative 5, and so on. If you're doing it by hand, then I would say let's get like a by itself up here, so subtract the b over, and then plug it into this bottom equation. So that you get negative 69 equals negative 24 minus 6b minus 3c. So you add the 24 over, which gives you negative 45. And then we can eliminate with this equation up here, this blue one, because it has a b and a c as well. So either we need to multiply this blue equation by 3, or technically we could divide this one by 3, whichever way you want to do it. So I'm going to multiply by 3. Negative 15 equals negative 9b plus 3c, which gives you negative 60 equals negative 15b. So b is 4. And then that, from here, now that we've done all that work, it's a lot easier to get a and c, because plug the b in here, and you figure out that a equals negative 8, and we can plug in b here in this blue equation, or we can plug in a somewhere, doesn't really matter. Negative 5 equals negative 3 times 4 plus c. So that's negative 12, which I add over so that c is 7. And then we just have to write out the answer.
Where did you get the negative 15 equals negative 9b plus 3?
Negative 15, where?
The green, the right. Yeah.
I took this equation and I multiplied it by 3 so that I could eliminate. So our answer is a was negative 8 over x minus 3. And then b is 4, so that's 4x plus c, which is 7, and that's x plus 6 on the bottom. And again, if you take the original and graph it, and you take this and graph it, you should end up with the same thing on your graph. Okay. Systems of linear inequalities. This is 27. You can feel free to use your calculator to help you with this, but you are having to put it on a graph on your paper. So the table of values might be helpful. On the second one here, we would need to, if we plug it into our calculator, to solve for y. And so the first one is a parabola at 0, 0. And the second one is a line that goes through 5 and has a slope of negative 1. And both of these are equal to, so both of these are solid lines. And our answer is actually where we would shade that these two solutions overlap, because greater than x squared is inside of our parabola, so in here, and less than 5 minus x is underneath our line. And so our answer is where those overlap, which is right here. It's inside the parabola, but underneath the line. And you can shade both of those and then shade darker where they overlap, or whatever it takes. Then if you pick a point in here, by the way, inside of where you think it's shaded, if you plug those in, you should get true statements, and that's how you shade it in the right spot. This is a circle with a radius of 4. And so it's really easy to just remember that instead of having to solve it for y and plug it in. If it's less than or equal to, that means we're shading inside of the circle. And then we have a line. Y is less than -2 minus x, so we go down here to -2 and have a slope of -1, and that is a dotted or dashed line because not equal to. So it's inside the circle and it's less than the line we drew, which means that we would shade the bottom left half-ish of our circle. And the last problem we have is the very last thing we did in 7.5. So if you haven't gotten there yet, shame on you, but we need to do this the way we talked about doing things in 7.5. This is a linear programming problem, and so you start off by writing a set of equations with an objective function, which has to do with the money that we're either trying to make or trying to, like, our costs. And in the problems in the book we had costs, but this one is we're trying to make money by selling 2 different types of rings. So we have $40 for one type of ring, so 40 times x. We have $35 every time we sell the other type of ring. So we can set up an objective function that in this case we're trying to maximize. This is going to give us profit. And it is helpful maybe to say, okay, because of the way I wrote this, x is the number of VIP rings we're going to make, and y is the number of SST rings we're going to make, whatever that means. They give us in the problem constraints, things that we have to work with. So they tell us that they can produce up to 24 rings each day, so that means less than or equal to 24 is one of our constraints, and that's basically on the number of rings. And then they tell us that they can use up to 60 total man hours, so that means we have to be less than or equal to 60, and this equation is talking about hours. So they don't actually tell us anything else about the rings, so we have to kind of know, hey, that just means I need to do x plus y. Like the total rings I make, x plus y has to be less than or equal to 24. They do tell us that it's 3 man hours for VIP, so 3 times x, and it's 2 man hours for ST, so that's 3x plus 2y is less than or equal to 60. And then because we're in the real world and we can't negative rings, x and y both have to be bigger than 0. Okay, so now we are going to graph what I have in blue. We're in the first quadrant. So I look at this and I'm for graphing by intercepts. So if I cover up the y here, my x-intercept is 24. If I cover up the x, that means my y-intercept is also 24. So I can draw that line going between 24 and 24. But I'm going to go ahead and keep going so I know what kind of scale I need. So here, if I cover up y and I divide both sides by 3, that means my x-intercept is 20. If I cover up s and divide by 2, that means my y-intercept is 30. And because I did that, now I know that my scale really only needs to go out to 30 in either direction. first line goes through 24 and 24. And it's because these are both positive in front of y, I can take this less than or equal to. It is less than this line. Okay, so I'm going to shade down and left. This one, 20 and 30, so that's an x-intercept 20 and a y-intercept of 30. It is good that these lines cross, like that's something that normally happens, so if your lines don't cross, that's a bad sign. And it's also less than that line, so the region we're talking about is this region right here. That's below both of those lines, but only in the first quadrant. What this is saying is you could pick any point in the region that's shaded black, and it would solve all of these inequalities and give you true statements. But what we want is to maximize our profit, and so there are a certain set of points that we can use. Test real quick that one of those has to be a maximum if there is a maximum at all. And those points that we're going to use are the region, like the corners of this region where we shaded. And so this point we don't know yet. The point down here in blue, that was 20, 0. We technically also have this point, which when I worked it out on the review, I think I forgot about. That 0, 0, that's not going to be the max because that means we're producing nothing. So obviously that would not be a max. Over here on red, that's the point 0, 24. We just need to find this point, and honestly, that almost always is going to give us our maximum. Because typically, with the setup of a problem, does it make sense that we should only fit one type of ring? Like, otherwise, why are we doing this, right? It should be some combination of the two types of ring. So to get what that intersection is, we would solve the system of equations. Okay, or if you drew your scale well enough, or if you graphed it in your calculator, there's lots of ways. We just need to find what x and y are. So I'm going to eliminate my y. So I'm going to multiply the first equation by -2. That tells me x is 12, and if I plug that into the first equation, that means that y also has to be 12. So, to find the maximum, I plug in these points around the region I shaded, and whichever one gives me the biggest number, that is our maximum bit. And our objective function up there at the top is 40x plus 35y. Now I plug in 0, 24, 12, 12, and 20, 0. And we could plug 0, 0 as well, but hopefully we all know that that's going to give us 0, which is not going to be the right answer. And 35 times 24. Okay. 40 times 12 plus 35 times 12? 900. And then this last one should just be 800. And so this is saying that our max profit is $900 at 12, 12. Okay, and so we're saying that's 12 VIP rings and 12 SST rings. That's how many we should produce of each. And that's pretty much the test.